Hello, I'm your host, Dr. David Urban, and I will be guiding you through Brown and Poon's Introduction to Organic Chemistry, 6th edition. The slides were downloaded from the Wiley Instructor Companion site and are copyrighted by Wiley. The commentary is my own. I have divided each chapter into smaller sections to make it easier to view on a wide variety of platforms. So let's begin. We'll continue with Chapter 2, Part 3, Acids and Bases. Okay. So we've already talked about Arrhenius acids and bases and Bronsted-Lowry acids and bases. I want to take you even to a broader term for organic acids that we will use a lot of in the organic chemistry course, the rest of this course. So the idea here is that we have what are called Lewis acids and bases, okay? So in a Lewis acid or base, that's any molecular ion that can form a new covalent bond by accepting a pair of electrons. Notice we're not transferring a proton, we're not reacting with water. We are creating a bond by accepting a pair of electrons. Okay. Now that means that in contrast, a Lewis base would be any molecular ion that can form a new covalent bond by donating a pair of electrons. Okay. So let's look at that again in a little more detail right here. If we have a Lewis acid, it wants to accept a pair of electrons to form that new bond. And if we have that Lewis base, we want to donate the electrons from it. So if we think about this, a Lewis base might have a lone pair where it can donate to the Lewis acid, creating our new bond. Now, if both of these were neutral at the time, that means we're going to form charge in our final material. And notice, like most acids and bases, there is possibility for an equilibrium to exist. Okay. So let's take that and look at it a little more intensely, and let's look at it from the idea of HCl dissolving in water. In the Arrhenius definition, the proton forms hydronium ion. In the Bronsted-Lowry, a proton is transferred. Let's look at it in the terms of Lewis acid base theory. Okay, so in the case of this, we have water right here that can act as an electron pair donator. So this can donate a sent electron pair to create a new bond with the hydrogen here. The hydrogen is the electron pair acceptor, okay? So in the case of the Arrhenius acid, we are creating hydronium ion. In the case of Bronsted-Lowry, we are transferring a proton. But in the case of this, the hydrogen is our Lewis acid because it accepts a pair of electrons to create that new bond, to form the hydronium ion. And the base in this case is water because it has a pair to donate to that new bond. Okay. So let's look at that in a different way. Okay, so in the case of, let's take it away from water. So we're moving it away from Arrhenius and transfer it to more of a Bronsted-Lowry kind of base here. We have a proton that still can be transferred, but let's, instead of using water, we're going to use methanol right here. In the case of methanol, we have a lone pair that can be a lone pair donator to form that new bond, that new covalent bond. And we still have hydrogen here as our Lewis acid, which is our electron pair acceptor. Once we do that, we create a new covalent bond and a charged species, this oxonium ion here, but we've completely eliminated water, so it cannot fall under Arrhenius. We've only done, but we have transferred a proton, so it still falls under Bronsted-Lowry. But in the case here, our methanol is our Lewis base because it has electrons to donate to making that new bond. Okay, let's look at this one more time by looking at different Lewis acids and Lewis bases, specifically Lewis bases, and what they can have in their relative strengths and their relative proton transfers. Okay, so why do we look at these Lewis bases first? Because the Lewis bases are the ones with the lone pairs that are donating to create that new bond. Okay, so if we have halide ions here, these are Lewis bases because it has 4 pairs of electrons that it can donate to make that new bond. Okay, and we consider these very weak Lewis bases because they have the lone pairs and they have a stable charge. Okay, the next set we have here are what we call weak Lewis bases. These Lewis bases have lone pairs. They are neutral molecules, but they still have lone pairs that they can donate to make those new bonds. Once they donate those pairs, they create ions, and therefore they are considered weak Lewis bases. Okay. Now, once we move those electron pairs away off of oxygen and move them onto nitrogen, we tend to get stronger Lewis bases. So here, in the case of ammonia and the amines here, the lone pair is now on nitrogen, and these lone pairs are a little bit easier to donate, therefore that makes them a stronger Lewis base to form that new covalent bond and a positively charged amine compound, okay? The next stronger here is ones with the oxygen where we already have the lone pair. Now that we have the lone pair and a negative charge, once we do donate that electron pair to form that new bond, we have a neutral species produced, which makes it an even stronger Lewis base. Which brings us to the strongest Lewis bases on this series here, and that's where we have the nitrogen that has that lone pair, but it also has a negative charge, so it ends up having 2 lone pairs. So it starts with a negative charge, and it still wants to donate those electrons to form a neutral species at the end, and these are very strong ions. We do have stronger Lewis bases, but in this series, we see going from the halides through the neutral oxygen-containing species are stronger. The neutral nitrogen-containing species are even stronger. The oxygen with a negative charge gets stronger, and then the nitrogens with this negative charge are the strongest in this set. So what does this mean for us right here? And how are we going to use this here? Okay, so in the Bronsted-Lowry system, we have to transfer a proton. Okay, so the acid is defined by transferring a proton. But in the Lewis species, we don't have to transfer a proton. Okay, which means in the case of a Lewis acid where no proton is transferred, we can actually form organic cations that are formed when only 3 bonds are formed to the carbon and leaving an empty charge that is there to accept electrons, okay? So that means in the case where we have only 3 bonds to carbon here, and we have an empty orbital, it is willing to accept electrons to form a new covalent bond. So in this case, the carbocation is our Lewis acid wanting to accept those electrons, and the bromide ion is our Lewis base because it can donate those electrons to form our new covalent species. And notice since we had a plus charge here and a minus charge here, our final product is a neutral species. Okay. So now we've completely eliminated the need for a proton transfer. The only thing that's happened is electrons were donated by the base to the acid to create that new bond. So that brings it in the broadest, most form of what we can call an acid or a base. Okay, but what does that mean about Arrhenius and Bronsted-Lowry? Does that mean they're wrong? It's like, no, they aren't. We can apply those same rules of Lewis acid base to the Arrhenius and the Bronsted-Lowry system. So for example, in the case of hydrogen, hydrogen plus is a Lewis acid because it's accepting a pair of electrons. It's accepting a pair of electrons to create a new covalent bond, okay? So it is a Lewis acid. And in the case of the Arrhenius situation, we have water, is a weak Lewis base. It has the lone pair to donate. The Lewis base is donating that pair of electrons. So in the case of Arrhenius, the hydrogen is still a Lewis acid and the water is still a Lewis base. Okay, we're just thinking about it in a different, more broad sense. Okay, now in the case of Bronsted-Lowry, we have that the acid is the proton donor. Okay, now again, the acid is proton donor because that proton is accepting a pair of electrons. Okay, now it's accepting the pair because the proton that's being donated is forming that new bond. Okay, so the acid is still the proton donor, but because the proton is accepting that pair of electrons. The base is a proton acceptor because the electrons from the base are used to donate to make that new bond with hydrogen. Therefore, it's still donating an electron pair. So Arrhenius is still applies to all Lewis acids, but not all Lewis acids are Arrhenius acids. And likewise, all Lewis acids are Bronsted-Lowry acids, but not all Bronsted-Lowry acids are Lewis acids, which means in the broadest sense, Lewis acid-base theory encompasses all organic molecule acid-base reactions plus all Bronsted-Lowry plus the Arrhenius aqueous system. Okay, so the net result out of this acid-base chapter is all organic molecules can be described as a Lewis acid or base. Either it's willing to accept electrons or willing to donate electrons. Acid strength is still influenced by the electronegativity of the atom, resonance stabilization, the inductive effect of electronegative atoms nearby, but not necessarily bonded to that atom, and the size and delocalization of charge. For example, iodine gets bigger and bigger, it becomes a stronger and stronger acid or a weaker and weaker base. And whenever we have a strong acid, we have a weak conjugate base, and whenever we have a strong base, we have a weak conjugate acid. Okay. Now, the other thing to remember is we need to figure out kind of a trend of pKa's, not the exact value. We need to know that the acetylene proton is more acidic than an alkene proton, which is more acidic than an alkane proton, and where alcohols and carboxylic acids up here on that trend. Do not memorize the exact values, but know which is more acidic than the other in a general sense. All right, thank you. That concludes chapter 2, acids and bases, and we will move on to the next chapter in the next video.